All right, welcome back to Statistical Analysis in Psychology. This is week 12, class number 2, chapter 8, Introduction to the T-Test, Single Sample and Dependent Means. So this is where we're finally going to remove all the limitations. We're going to remove all the assumptions, those unrealistic assumptions that we've been making for hypothesis testing for educational purposes. And now we're going to get into the real life, real world, real way of doing hypothesis tests. So you'll notice that we have two types of tests that we're going to be taking a look at today. In this chapter. We're doing single sample and dependent means. We're going to start off today with just looking at single sample. So this is going to be day 2 of our face-to-face shutdown period. So thanks for coming back. Thanks for joining me again. And let's go forward with today's class. All right, so as we saw before, we're still dealing with that 5-step hypothesis testing procedure. So we're still dealing with step number 1, the null and research hypothesis. Step number 2, determining the characteristics of your comparison distribution. We finally got that in chapter 6. Step number 3, finding your cutoff scores. Step number 4, calculating your sample means z-score. And then step number 5, making your decision to reject or accept the null hypothesis. So you have all of those skills right now. So what we're going to do today is we're going to continue with that, and we're going to continue to get you ready to do this. We're going to continue to get you ready to do this alone. However, now we're going to move forward and get you into the real world. So we're going to get you to the point where you're going to be ready not to do it with any restricting assumptions, not to do it with any unrealistic assumptions, but you get ready to do this now for real. So we are finally taking that step so that we can become those statistical ninjas, so we can become those psychologists that get sent in and know how to handle data, have those skills to do the really cool stuff in psychology, the stuff where you can analyze real data from real studies and make real differences in people's lives. So we are going to revisit Harlow and his monkey study for this, but this time we're going to do it the way that Harlow would have actually analyzed his data. We're going to do it in a realistic way using the real skills that statisticians would use when they're doing a single sample hypothesis test. More on that right now. So what we're going to be working on today, there's going to be 2 parts to today's class. The first part is going to be a glimpse of what's to come. It's going to be a little foreshadowing of what's coming up in the future, what's coming up in part 2, which you are not going to want to miss. And then we're going to take a look at how we used to do hypothesis testing. And then we're going to introduce our first big move in going from unrealistic to realistic hypothesis tests. And that's going to be the T-statistic. And the T-statistic, you're going to see, works almost exactly like a Z-statistic. So all the practice we've been putting of the Z-statistic, you're going to be able to use that for the T-statistic. And then we're going to go forward and start doing a hypothesis test with the T-statistic. In part 2, we're going to revisit that hypothesis test with the T-statistic. We are then going to go into the future and we're going to introduce SPSS, which is a dedicated statistical package used specifically for statistics. And then we're going to mention some in-class practice, and that will be the end of our session today. So, coming with us into the future. As we continue to build our statistical skills and as we continue to get more and more realistic with our statistical tests, with our hypothesis tests, we are getting to the point where it's very difficult to do this with pencil and paper. It's very difficult to do this with Excel. It's very difficult to do this manually, step by step. So it's time to get rid of the old skills and move on into the future. It's time to introduce a dedicated statistical package for statistics known as SPSS. So what SPSS is going to allow us to do, it's going to allow us to offload all of that tedious mathematical calculations. It's going to have us offload all of those complex calculations to a tool that does those rather well, which is a computer. And what that's going to do is it's going to leave us the task of selecting what hypothesis test to do, setting it up correctly in SPSS, and then once the numbers are crunched, once the test is run, interpreting that data correctly so that we can come to the correct conclusions. So we're going to have the machines do what machines are good at, which is that data crunching calculations. And then we're going to use our human minds to do the difficult analysis of interpreting and setting up the data for the test. So when last we were talking about hypothesis tests, we were always talking about a known population. So all of our previous hypothesis tests dealt with a population that we knew the mean for and we knew the standard deviation of. And from that, in chapter 6, we learned how to calculate the comparison distribution, your distribution of sample means from your known population. And from that, we would take a sample, we would treat it, and then we would discover for that sample mean, for that treated sample mean, what's the probability that it actually still came from the distribution of sample means? What's the probability that it still belonged to that distribution? And we would set up our cutoff scores, and it would have two tails, which contain the highly unlikely samples, the samples that are just way too unlikely to have occurred randomly. And then what we did is we calculated our sample's z-score, found out where it was in that distribution of sample means, and made our conclusions based on whether it stayed in the body, as you see here in this slide, where we would accept the null hypothesis, or did it move into the tails, in which case we would reject the null hypothesis. Now, all of this required that we worked with a known population. And because of that, we were able to calculate a z-score. What we're going to do today is we're going to go to our first realistic style hypothesis test, and we're going to, instead of having a known population where we know the mean and we know the standard deviation, we're going to have what's called a hypothesized population, where we hypothesize about the population mean, but we have no idea what the standard deviation of that population is. Now, this hypothesized mean can sometimes be a little tricky. It's always theory driven. It's what would be true if the null hypothesis was correct. It is the population mean that would exist if the null hypothesis is correct. So I'll give you an example of this that might help you understand. People that investigate the pay gap, people that are looking at the gender pay gap, when you take a look at the data that's coming out of the gender pay gap studies, there's a wide variety of different estimates for what the gender pay gap was. I've heard estimates as high as 50 cents for the dollar, meaning that women make 50 cents for every $1 that males make. And I've heard it all the way up to 99 cents for the dollar, that women make 99 cents for every $1 that males make. So here we have a little chart showing the progression of the gender pay gap from 1970 to 2016. But importantly, it also gives us a hypothesized mean, because if we had no gender pay gap in a world where the gender pay gap was zero, where there was no effect of gender, where there was no treatment effect, where there was a null result, in a world where the gender pay gap had no effect, then we know what that gender pay gap is in that world, and it is 0%. So where women make 100% of what males make. So we might not live in that world, but we know that if we didn't have a gender pay gap, that would be the situation. That would be the hypothesized mean, that women make as much as males make. So that's a good example of this idea of a hypothesized mean. It's not necessarily what's true. It's not necessarily the real number, but it's what would be true if the null hypothesis was correct. What would be true if the null hypothesis itself was true? So just to one more time make this point, just as the gender pay gap in 2016 was 79 cents, right? So women only make 79 cents of every dollar that males make. In a world where there is no effect of gender pay, we know what that world looks like. And it looks like the two genders making equal money. So that is your idea of a hypothesized mean. What would be true if the null hypothesis was actually true? So we have a hypothesized mean. We have an unknown standard deviation. We don't know what the spread of our unknown population is. And because of that, we're going to run into a problem here, because we need to calculate our distribution of sample means, but now we're dealing with an unknown population. And in this unknown population, we're missing numbers, right? We don't have the standard deviation of the population to plug into this formula. So if we cannot calculate the comparison distribution, that means that we can't calculate the z-score that we need in order to do our hypothesis test, and we've reached an impasse. We need a new solution. And the new solution that we use is called the t-statistic. So the t-statistic is an alternative to the z-statistic, and we do it for unknown populations. So in this case, we're going to use it for an unknown population where the mean of your population is hypothesized. So again, that gender pay gap, we don't know what it is, but if we lived in a world, in a population where gender pay was equal, that pay gap would be 0, right? So the hypothesized mean for this unknown population, and importantly, an unknown standard deviation. So because of that, we can't directly calculate the parameters for the distribution of sample means. We can't use the formulas that we used in chapter 6, where the mean of your comparison distribution equals the mean of your population, and the standard deviation of your comparison distribution equals the standard deviation divided by of your population divided by the square root of the size of your sample. So what we're going to do is we're going to have to introduce this t-statistic, and very thankfully, we're going to introduce it in just a bit, but very nicely, it doesn't change the 5 steps very much. So those 5 steps are still the 5 steps. The 5 steps that we use for hypothesis testing, those are still the 5 steps that we're going to use for the t-statistic hypothesis test that we're going to do right now. So step number 1, restating the question as a research hypothesis and a null hypothesis about the population. This absolutely does not change from before. So all the skills that we learned about how to formulate a null hypothesis and research hypothesis, those all, no change. Those all stay exactly the same. Keep doing what you were doing. Determining the characteristics of the comparison distribution, what we just learned in chapter 6, that actually changes. Changes a little bit, doesn't change too much, but be aware it does change. Step number 3, determining your cutoff sample score on the comparison distribution that you're going to reject your null hypothesis, calculating your lines in the sand. This actually changes. And it's not a big change either. What we're going to do is we're going to flip from Appendix 1 to Appendix 2. So be aware that we're going to be doing that. We're going to go to the t-statistic tables rather than the z-statistic tables. Determining your sample score on the comparison distribution. This is a super slight change. This is a kind of blink and you'll miss it change. So again, basically what we've been doing before, we'll just point out which values you should be using for this step now. And then finally, step number 5, decide whether to reject or accept a null hypothesis. This doesn't change. This stays exactly the same. All right, so let's take a look at what is actually changing. So step number 2, determine the characteristics of the comparison distribution. What we're going to do, what the move is that we're going to use, is we are going to use our sample to estimate parameters about our population. So just like we were setting this up before, where you measure a sample so you know something about a population, since we don't know anything about our population, we do have our sample. So we can use our sample to estimate what we're missing from the population. Specifically, we're going to estimate our population's variability by using our sample variability. So population variance, the formula for that was the sum of squared deviations. Remember that tricky one? Sum of squared deviations, not sum of squares. Sum of squared deviations divided by the size of your population. Population standard deviation is the square root of your population variance. And that population standard deviation was what we used to use to calculate the comparison distribution's standard deviation. However, we don't have that value anymore. But what we do have is a sample. So we're going to take sample variance and we're going to use that to stand in for population variance. So sample variance, if you remember back week number 2, is the sum of squared deviations divided by n minus 1. So n is the size of your sample. So sum of squared deviations divided by the size of your sample minus 1. This size of your sample minus 1 commonly occurs. Remember I told you the universe loves the minus 1. Minus 1 pops up all over the universe. And this size of your sample minus 1 has been given a special name. It's called degrees of freedom. So remember that degrees of freedom is size of your sample minus 1 in this case, and your sample variance equals your sum of squared deviations divided by your degrees of freedom. What we need, though, is that sample standard deviation, and that is just the square root of the sample variance. So we can calculate the sample variance. We have a sample, we have numbers, so we can calculate that sample variance. And what we're going to do is we're going to estimate that unknown distribution of sample means, standard error, with the estimated standard error. We're going to do the same thing that we did in Chapter 6, except instead of using the population standard deviation, we're going to sub in the sample standard deviation. So instead of calculating the standard error, we're going to calculate the estimated standard error. So standard error, the formula for that was the standard error equals standard deviation of your population divided by the square root of the size of your sample. Your estimated standard error looks almost exactly the same because we're just subbing in the sample standard deviation for the population standard deviation. So we have the size of your sample, the estimated standard error equals your sample standard deviation divided by the square root of the size of your sample. So it's the exact same type of formula. We're just using sample standard deviation in place of your population standard deviation. All right, so that was that move. Step 3, determining the cutoff sample score on the comparison distribution, finding those lines in the sand where you draw your lines and you make your tails, whether it's one-tailed or two-tailed. That actually changes. And the reason that it changes is because the distribution of sample means, our comparison distribution, is no longer a z-distribution. So because we're using estimated, because we're using the standard deviation of the sample to estimate the population, we actually lose the shape of the z-distribution. So our comparison distribution no longer looks like a z-distribution, which means that we cannot go to Appendix A1. So what do? Well, the distribution that it actually creates is known as a t-distribution. And a t-distribution has two slight differences from a z-distribution. First off, a t-distribution has more area, a larger proportion of it in the tails. So you can see in this t-distribution here, the tails are fatter, they're bigger, they're larger than the tails of the z-distribution. The other difference between a t-distribution and a z-distribution is that a t-distribution changes depending upon the size of the sample. So a t-distribution with a degree, with 1 degree of freedom, that comes from a sample size of 2. And you can see right here what it looks like. It's thicker in the tails, it's a little bit narrower in the body. When we go up to a sample size of 3, so that we have 2 degrees of freedom, remember 3 minus 1 equals 2 degrees of freedom, we see that the t-distribution has changed. And when we increase the sample size again to 4, so that we have 3 degrees of freedom, we see that it changes again. And it'll change for 4 degrees of freedom, and 5 degrees of freedom, and 10 degrees of freedom. And notice that as the degrees of freedom get larger and larger, it is looking more and more like a z-distribution. So a t-distribution, its shape depends upon the degrees of freedom. So it's very important, number 1, to flip to the right appendix. Make sure you're flipping to the t-distribution appendix. And number 2, make sure that you know what your degrees of freedom are. They're the size of your sample minus 1. So 10 degrees of freedom happens for a sample size of 11. 20 degrees of freedom happens for a sample size of 21. All right, so this new distribution means a new table of values, your t-distribution table, and that's where we're going to be looking up our lines in the sand. That's where we're going to be looking up our cutoff scores. All right, step number 4, determine your sample score on the comparison distribution. This is a slight change. This is a blink and you'll miss it change. So let's take a look at it right now. Your formula for the t-statistic, you have to take your sample mean and change its raw score into a t-distribution score. Just the same way we took the mean and transformed it into a z-score, we now have to take the mean and transform it into a t-score. Sounds exactly the same? It actually looks exactly the same. So there's a formula for a t-statistic, your sample mean minus your population mean, all divided by the standard deviation, the estimated standard error that is the standard deviation of your comparison mean. That looks an awful lot like the z-score that we've been using this whole time. So just to put it in, back it up a little bit in that same formula, that estimated standard error is your standard deviation of your sample divided by the size of your sample. The z-score, standard deviation down here, is the population variance divided by the size of your sample, and all of that taken by a square root. So the important part, I'm kind of flubbing it a little bit here, but the important part here is that it's the same move. It's the same type of formula. You can take a look at the top. It's exactly the same. It's the deviation from the sample mean and the comparison distribution's population. And that is divided by the standard deviation of your comparison distribution. So it's exactly the same. It's just that now we cannot use the z distribution. We have to use that t distribution. All right, so we have those changes. So now here's the situation that we have. We have an unknown population. However, it's got a hypothesized mean. We know what this population would look like if the null hypothesis was true. We know what that null hypothesis being true would look like. What we don't know is we don't know the spread. We don't know the standard deviation of this population. So it's an unknown population. From that, we create our comparison distribution. Now our comparison distribution is a t distribution, has the same mean as our hypothesized population, but we use our sample to estimate the standard deviation of the population so that we can get the standard error of our comparison distribution, which is the standard deviation of your sample divided by the square root of the size of your sample. And once we have that comparison distribution, the logic follows exactly the same. We're going to determine what is the probability that the mean of our treated sample still belongs or still came from that distribution of sample means. And we are going to look up a table. We're going to draw our lines in the sand. We're going to calculate a t-statistic. And if the sample ends up in the body of the t-distribution, if it does not cross into the tails, it does not cross beyond our cutoff scores, we're going to accept a null hypothesis. However, if the sample goes into those tails, crosses that line, we're going to reject the null hypothesis and we're going to accept the research hypothesis. So much like we were doing before, we're going to use the same logic. And if our treated sample ends up in the tails and we conclude that it no longer belongs to the untreated unknown population, we will then conclude that it has changed enough so that it now belongs to a different population, a treated population. All right, so what we're going to do now is we're going to put this into action. We're going to go back to Harlow and the classic infant attachment study that he did, and we're going to see how he would have done that for real. So let's set it up one more time, this time with the actual kind of procedure that he would have used. So in a classic study of infant attachment, Harlow placed infant monkeys in cages with two artificial surrogate mothers. One mother was made from bare wire mesh and contained a baby bottle from which the infants could feed. The other mother was made from soft terry cloth and did not provide any access to food. Harlow observed the infant monkeys and recorded how much time per day they spent with each mother. In a typical day, the infants spent a total of 18 hours clinging to one of the two mothers. So they know that these monkeys, in general, spend 18 hours clinging to one of the two mothers. If there was no difference or no preference between the two mothers, you would expect the time to be divided evenly with an average of 9 hours for each of the mothers. This is a very important point. That is your null hypothesis. Your null hypothesis is that there is no effect. Your null hypothesis is that there is no difference between the two mothers. And then we need to use a little bit of logic. If the monkeys spend 18 hours with the mothers and there's no difference between how long they spend with each mother, then they're going to have to spend half the time with the terry cloth and half the time with the wire mesh mother. So 18 divided by 2 equals 9 hours with the terry cloth mother and 9 hours with the wire mesh mother. Now, we don't know how much time they actually spend with the terry cloth mother, but importantly, we know how much they would spend if the null hypothesis was true. We know how long they would spend if there was no preference. It's splitting that 18 hours into 2, and you get 9 hours with the terry cloth mother. However, as we can see, the typical monkey spent about 15 hours per day with the terry cloth mother, indicating a strong preference for the soft, cuddly mother. All right, so suppose that we had a sample of 9 infant monkeys, and they averaged 15.3 hours per day with a sum of square deviations of 216 with the terry cloth mother. So we're going to take this back to basics. We're going all the way, just so you can see all the bones, all the parts. We're going all the way back to the sum of square deviations, and we're going to start with that. Is this result sufficient to conclude that the monkey spent significantly more time with the softer mother than would be expected if there was no preference? And we're going to use a two-tail test with an alpha of 0.05. All right, let's get down to it. Hypothesis test with the t-statistic. 5 steps, same 5 steps. You'll notice these have not changed since we've begun hypothesis testing. So let's start with step number 1. Restate the question as a research hypothesis and a null hypothesis about the population. So the question we want to ask is there a preference for the terry cloth mother, or is there a preference for the wire mesh mother? Is there a preference for one of the mothers? So our research hypothesis is going to be that there is a preference for one of the mothers, and we can write this out as the mean time spent with the terry cloth mother does not equal the mean time spent with the wire mesh mother. And if that's the case, then our monkeys belong to this treated population where they prefer one mother more than the other. On the other hand, if there is no preference for the mothers, if the null hypothesis is true and there is no preference for the mothers, then the mean for the terry cloth, the mean time spent with the terry cloth mother is going to equal the mean time spent with the wire mesh mother. And that means that our monkeys belong to the unknown population, to that hypothesized untreated population. So once again, the research hypothesis, there is a preference, meaning that the time spent with the terry cloth mother does not equal the time spent with the wire mesh mother, i.e. one of them gets more time, i.e. there is a preference. Or the null hypothesis, there's no preference for either mother, and both mothers get exactly the same time spent with them. The time spent with the terry cloth mother, same as the time spent with the wire mesh mother, and that's our untreated hypothesized population. Step number 2, determine the characteristics of the comparison distribution. We have our mean of the distribution of sample means that is equal to our hypothesized mean, and that is equal to 9. And we get that number 9 by dividing the 18 hours that these monkeys are allowed to spend with the terry cloth mother and the wire mesh mother, and we chop that in 2. And we say, all right, half of it goes to the wire mesh mother, half of it goes to the terry cloth mother. That's what would happen if the null hypothesis was true. So that mean for your distribution of sample means, that mean for your comparison distribution, that is your hypothesized mean if the null hypothesis was true. So remember that as a very key point. It's your hypothesized mean if the null hypothesis was actually true. So we have our mean for our comparison distribution. We need our spread for our comparison distribution. And for this, we are going to rewind it all the way back just so that you can see kind of what this is built up out of. And maybe so you can also appreciate when we hand this all over to SPSS just how wonderful this program actually is. So if we want to calculate our sample variance, that S squared sample variance equals your sum squared deviations divided by n minus 1. That's the size of your sample minus 1. That's equivalent to the variance. Sample variance equals the sum squared deviations divided by the degrees of freedom. So we have all this information. Sum squared deviations was given to us in the question. That's 216. Size of our sample given to us in the question, 9. We had 9 monkeys. 9 minus 1 is 8. 216 divided by 8 happens to be 27. So that's the sample variance. That's all well and good. We need the sample standard deviation. So we need to take that sample variance and we need to divide it by the size of our sample and then take the square root of the whole thing. This is what we learned in chapter 6. And if we plug in those numbers, we see that we get our estimated standard error. The standard deviation of our comparison distribution is √3 or 1.73. So we have now the characteristics of our comparison distribution. We did it all by ourselves thanks to chapter 6. So now what we can do is we're going to go to step 3, and we're going to set a cutoff sample score or a critical value. So these are the lines in the sand that we've been talking about. This is where we say this is how far our sample is allowed to go. So for us to still believe it belongs to the hypothesized population, it belongs to that null hypothesis population. But if it goes past that line, then we're not going to believe it anymore. And we're going to say, nope, there's a treatment effect. We're going with the research hypothesis. So we need to figure out those lines in the sand. And it's going to be very similar to what we've been doing, but importantly, it's a t-distribution table. So what we're going to be doing is basically the same thing we've been doing this whole time, but instead of flipping to table A1, we're going to flip to table A2. And here's table A2 over here. Now, in this table, it's set up much like the z-distribution table. However, because of that added difference for t-distributions that they change with degrees of freedom, this table is actually set up where you need 3 pieces of information in order to find your cutoff t-statistic, in order to find your cutoff scores. So the first piece of information that you need is you need to know, is this a one-tailed or a two-tailed test? So for our experiment right now for Harlow's monkeys, we're using a two-tailed test. So we're going to want to concentrate on that area of the table that is dedicated to two-tailed tests. The next piece of information we need is we need to know what are the degrees of freedom. So we have 9 monkeys in our study. 9 minus 1 equals 8 degrees of freedom. So we're going to stay in that two-tailed test area of the table, and we're going to concentrate on the row that has that is there for 8 degrees of freedom. And then the last thing we need to know is, what is the alpha level? What was that alpha level that was given to us for our hypothesis test? And in this case, it was 0.05. So we go down to the 0.05 column, and that's our final piece. And where all of that information intersects, basically at 2.306, that's your cutoff score. That's your line in the sand. So we found our cutoff score. We know that we found it from our table using those 3 pieces of information. So now we have our lines in the sand. And the way that it's typically written is T, and then in brackets, you put the degrees of freedom, because that's important for a T statistic. So T with 8 degrees of freedom equals plus or minus 2.306. Those are our lines in the sand. What we need to do now, we have our lines in the sand. We need to figure out, did our sample cross that line? Did our sample go beyond one of those lines in the sand? And in order to do that, we need to calculate our sample's score on that comparison distribution. So we need to do step 4. We need to find out where our sample mean is if we translate that sample mean into a t-statistic. We translate it into a t-statistic. Same way we used to change these things into z-statistics, we've now got to translate it into a t-statistic. So thankfully, this looks almost exactly like what we did with the z-statistic. So we have our sample mean. So our monkeys, on average, spent 15.3 hours per day with the terry cloth mother. Our comparison distribution has a mean of 9 and a standard deviation of 1.73. We found that out in part 2. So we use our t-statistic formula here. We plug in all that information, and we get a t-statistic of 3.64. And now the last thing we need to do is we need to do step 5 and decide whether or not to reject the null hypothesis. And if the sample t-score is beyond the cutoff t-score, we're going to accept the research hypothesis and we're going to reject the null hypothesis. And for this, just because I don't have the ability here to do this kind of live with a whiteboard, make sure that you're drawing this out. So make sure that you still continue to draw out your t-statistic, draw those lines, find out where your sample is, and then determine if the sample t-score is beyond the cutoff t-score, we're going to accept the research hypothesis and reject the null hypothesis. If the sample t-score is within the cutoff t-scores, we're going to accept the null hypothesis and we're going to reject the research hypothesis. As it turns out, our sample t-score is 3.64. That went beyond our cutoff t-score of 2.3. So if it goes beyond, we're on this slide right here. The sample t-score is beyond the cutoff t-score. So we decide we're going to accept the research hypothesis and we're going to reject the null hypothesis. And that is exactly what we did. We rejected the null hypothesis. And this allows us to conclude that these monkeys actually do prefer the terry cloth mother. The null hypothesis is not true. They actually do like to spend more time with the terry cloth mother. And this result was monumental in changing our views of parenting and infant attachment and what is important in terms of providing an infant with care and psychological well-being. All right, so that was the part one in the books. So part one was your sort of introduction to the t-test. And if you need a little bit of time to let that sink in, I highly recommend pause the video at this point, walk away, let it kind of just, your mind mull over it, and then come back, because what we're going to be doing now is we're going to be doing the same hypothesis test, but this time we're going to hand it over to SPSS. This time we're going to give it to the machines so that they can do the hard number crunching. They can do all that, dividing the sum squared deviations, by the size of your sample minus one. They can do all that stuff and leave us to do the human work of making sense of all of that information. So once again, this goes back to making sure that we have all 5 steps to do this in the real world. Number two, this goes back to the fact that it's getting too complicated. You saw just now how complicated all of that math was, all the multiple steps we had to do. So we have to, at this point, make that move, make that transition, develop those skills to use SPSS so that we can continue to do the more challenging hypothesis tests that are on the horizon. And again, this is exactly what computers are great at. They're great at doing computations. They're great at doing calculations. They're very exact. And then we're going to do what we're great at as humans, which is coming up with the questions, formatting them correctly, putting them into the computer, and then interpreting the results and figuring out what it all means. So for this, we're going to go back to Harlow's monkey study one more time. And this time we're going to analyze the exact same data, and we're going to see how it would be done if we were doing it with SPSS. And you're going to see it's going to be a whole lot easier. All right, so for this part 2, just to remind you, we're going to just briefly recap hypothesis test with the t-statistic. Then we're going to introduce SPSS. You're going to love SPSS. It is a very intuitive, much like Excel type of program. And then I'll mention the in-class practice that hopefully you can finish. And then if you have any questions on it, feel free to drop in on one of those online office hours, and we can go over it at that time. Now, before we begin with SPSS, this slide is actually rocketed in terms of importance. You need to have this resource to do this to do this type of work at home. So now that we're all at home, now that we cannot go back into campus, this becomes vitally important. Excel, I mentioned this previously, Excel is available for free. You can download Excel, you can install Excel on your home computers for free. Go to IU Anywhere, you can find it there. Go to 1IU and just search for IU Where. That's where you can find the programs that you can install on your home computer. SPSS is different though. SPSS, you have to go to IU Anywhere. So IUSB does not have the license for you to install this on your home computer, but what it does have the license for is for you to stream it from a computer that has the license. So a cloud computer that we have the license for streaming. So again, for this, go to 1IU, search for IU Anywhere, and you will be able to set up your account. You can log in using your IU ID, and then you're going to see in your when you get there, there's a way to search for programs. I would highly recommend search for SPSS, and then you'll be taken to a list of SPSS, and you will be able to do that. And you know what? I'm kind of talking about that a lot here. Why don't I actually show you what I mean just real quick? All right, so what you're going to want to do is you're going to want to go to 1IU, and in that search bar, you're going to type in IU Anywhere, and you can see it's right there in your tasks. So click on that, and that'll take you to the IU Anywhere link. click on Start, and that'll take you to the IU Anywhere sign-in page. And then simply log in using your IU login. I'm already logged in, and you'll be taken to this page. If this is the first time that you're using IU Anywhere, this will be blank. And the reason this will be blank is because, as you can see up here in this tab, this is the favorites. So as you keep using apps over and over and over again, you're going to want to add those to your favorites so that you have easy access. And you can see that I've added SPSS twice, version 25 and version 26. One way to find SPSS is to just search through all the apps. A better way to find SPSS is to go to the search bar here where it says search all apps. So if you just plug in SPSS there, you're going to see that we have version 25 and version 26. Ignore these ones that have these little tree diagrams on them, tree icons. You want the ones that have the circle here. So click on 26, let's use 26, and then make sure that you have your Citrix receiver installed. Make sure that you have opened all access for your computer to access the cloud server. If you need help with that, contact the IT help desk, and they will be able to get that going and set you up. But you do want to be sure that you permit use so that it can talk to the computers at the cloud computing. You can tell I'm very technical with this. It can access the cloud computing. All right, so this is what SPSS looks like. We're going to get into all the details for SPSS. Just right while I have it here, I'll point out a few things. This is your sort of welcome dialog box. This is where you can use a lot of, you can get a lot of good information here. Most importantly, I want to point you down to this little area here where you have Get Help and Support and Get Started with Tutorials. One of the best things about SPSS is that it is widely used. I chose this statistical package because it's probably one of the 3 statistical packages that are used the most. So there are tutorials built in to the SPSS program. There is help and support built into the SPSS program. There is a never-ending stream of YouTube videos showing you how to use the SPSS program. So while you're at home, unable to come into IUSB to get some face-to-face help, just know that you have 24/7 access to help with SPSS. Go online, go on YouTube, put in what you're trying to do with SPSS, and I guarantee you'll be able to find a video for that. Now, you have this video right here, but again, if you need a different perspective, there is tons of help. What we're going to do is we're going to close this little welcome bar, and then we're going to maximize our SPSS data editor here, and we're going to get back to that in just a moment. So that's how you access SPSS. I would highly recommend make sure, give that a try as soon as you can to make sure that everything is working and everything is open and ready to go. I have extended the deadlines for this homework, but do make sure that you're doing your part and contacting people that you need, the help desk, to make sure that you have this set up and ready to go. All right, so back to the hypothesis test. So same hypothesis test as before. I'm not going to reread it. We just went over it. Importantly, though, again, 18 hours is the maximum time that these monkeys spent with the two mothers, the terry cloth mother and the wire mesh mother. That means that if there is no preference between the two mothers, they will spend half of that time with each. So half of 18 is 9 hours with the terry cloth mother, 9 hours with the wire mesh mother. That is the null hypothesis. And if it helps, remember that gender pay gap. So we don't know exactly what the gender pay gap is today. I've heard estimates all over the place. But we do know what the gender pay gap would be under the null hypothesis. If there was no effective gender, then we know that the gender pay gap would be 0, right? There would be no gap. So keep that in mind when you're thinking about your hypothesized mean. You need to find that information in the question so that you can figure out what that hypothesized mean actually is. So if there was no preference between the two, they're going to spend 9 hours with each mother. However, the typical monkey spent 15 hours per day with the terry cloth mother. So we are going to do a two-tail test to see if that was significantly different. If the monkeys actually spent significantly more time with the softer mother than would be expected if they had no preference whatsoever. All right, so back to our question. Some of this we've already done in part 1, but it's always good to see it one more time. So let's go through it one more time. Step number 1, restate the question as a research hypothesis and a null hypothesis about the population. Is there a preference for the terry cloth mother or for the wire mesh mother? That's what we want to know. So the research hypothesis is that there is a preference. There is a preference for one of the mothers. The mean time spent with the terry cloth mother does not equal the mean time spent with the wire mesh mother. Now this time we're going to go a little bit further just to make it very explicit. We know what those numbers are. If the two mothers were equally preferred, they'd spend 9 hours with the terry cloth mother and 9 hours with the wire mesh mother. So if they're not spending equal amounts of time, then they can't spend 9 hours with the terry cloth mother. So we know that the research hypothesis can be written as the mean time spent with the terry cloth mother does not equal 9 hours. And if that is true, then these monkeys belong to a population where they prefer one of the mothers. On the other hand, if there is no preference for the mothers, we're in the null hypothesis. So the null hypothesis is that there's no preference for either mother. In this case, the mean time spent with the terry cloth mother will equal the mean time spent with the wire mesh mother. And again, we know what that number is. They have 18 hours to spend with both mothers. If they spend it equally, if there's no preference, they'll spend 9 hours with the terry cloth mother. And if they do, then these monkeys belong to this hypothesized population of no preference, mother-loving monkeys. All right. Step 2, determine the characteristics of the comparison distribution. Remember, we had to do all those calculations to find out the mean, to find out the standard deviation of our comparison distribution. Well, no more. SPSS is going to do all of that for us. So aren't we glad that we're introducing SPSS? Step 3, set a cutoff sample score or critical value. We need our lines in the sand. What we're going to do is we are going to crash PowerPoint. What we're going to do is we're going to mention that SPSS will not do this for you. So it can't do everything, unfortunately. However, it will help. And it's going to help by giving us the degrees of freedom. So we're still going to need to go to the table, but it will tell us the degrees of freedom so we don't make an error on that calculation. Step 4, determine your sample score on the comparison distribution. That T-statistic calculation that we've been doing, well, guess what? SPSS is going to do this for you as well. So you can see that a lot of the heavy lifting that we were doing in our hypothesis test is now going to be done by SPSS. So let's get to it right now. So we are going to open up SPSS. And the data that we're going to be using can be found in Week 12, Class 2 Practice, Chapter 8, Introduction to the T-Test. And what you're looking for is this data. This data right here. So I'm going to zoom in on this so that we can all see it. So that is the data that we're going to be using. And I'll make a very important point right now about SPSS. If you're going to use SPSS, you need to have the raw scores for each subject. That is a requirement. So these are the raw scores for each monkey. So monkey number 1 spent 17.2 hours with the terry cloth mother. Monkey number 7 spent 11.51 hours with the terry cloth mother. In order to use SPSS, you need those numbers. You need those raw scores. So that's one of the first things to know. So these are the raw scores that we're going to be using. And then one other thing that I'll mention before we begin is that there are screen grabs of this. They're from an earlier version of SPSS, but there are screen grabs in your lecture notes that will take you step by step through this entire procedure. So you have those in case you want to slow it down, in case you want to see, how this was done, kind of step by step. What we're going to do right now, though, is we are going to do this live. So we are going to just do this right now. So if you haven't already, I would pause the video, open up SPSS, go to IU Anywhere, make sure that your Citrus receiver is working so that you have that ready to go and you can follow along. All right, so what we're going to do here is we are going to set up this hypothesis test. So one of the big challenging things in SPSS is making sure that you format your data correctly. So we have our raw scores over here, and we need to take our raw scores and transfer them into SPSS. So one of the great things about it, though, one of the straightforward things, is that a lot of the keyboard shortcuts that work for Excel work for SPSS as well. So we're going to highlight the scores that we have. We're going to highlight the raw data, the hours that each monkey spends with the terry cloth mother, and we are going to go to SPSS and we are going to paste that directly into column 1, row 1. So we paste that there, and depending upon your firewall settings, depending upon your access settings, you might be able to directly paste into your IU Anywhere version of SPSS, or you might have to use a little toolbar that might be visible at the top of your video. So if you're having issues with that, I would recommend contact the help desk. Check out a YouTube video on Citrix receivers and SPSS, or drop by an office hour and I'll see if I can help you with that. All right, so we copied and pasted it into our into SPSS. So when you copy and paste data into SPSS, SPSS gives it a variable name. And it gives it a variable name that is very good for robots and really bad for humans. So the variable name that it assigned to our raw data is var 00001. And if you're a computer, that's excellent. That's a great variable name. If you're a human being, var 00001 means nothing. It will not jog your memory, and it will not help you do the cognitive work that we need to do. So what we want to do is we want to go down here where we can see we have tabs for our 2 views in SPSS. Currently, we're in the data view. That's where you do all your work with your raw data. What we want to do is we want to click on variable view, and that is where you can mess around with your variables. And what we're going to do is we're going to rename that var 00001 into something that makes sense for human beings. So we click on it and we simply write in tercloth, and that'll update the name of our variable to tercloth. So if you go back to the data view here, you can see that we've renamed it with something that makes sense to us as human beings. Now you might ask yourself something, well, why didn't we call it terrycloth? So let's take a look at what happens if you try to name a variable and SPSS doesn't like it. There's a lot of things that SPSS does not like. One thing that it doesn't like is spaces. So if you put in terry space cloth, it's going to give you this warning where it goes, your variable name contains an illegal character. You're going to get a lot of those warnings. SPSS is a little finicky sometimes. So if you get those warnings, just heed them, say, thank you, SPSS. I didn't know that offended you. So let me rework my variable name. So the other thing, though, is that you might wonder why we didn't put in terrycloth without a space. And the reason for that is that SPSS is in version 26, which means that there was an original version of SPSS back in, I'm assuming, the 90s. And then it just got built up on, decade, year after year, version after version. Because of that, it kind of has some old issues from its past. It's carrying a lot of baggage from like some of the early days of programming. And one of those is the length of variable names. So in some SPSS tests, if you have a variable name that is longer than 8 characters, SPSS is not going to like it. Now, in this test, you would be able to do it with a variable name longer than 8 characters. I highly recommend, though, just get into the habit of using a variable name that's only 8 characters long. It works everywhere. You're never going to run into issues. And in reality, tercloth is good enough to remind us that, oh, these are the scores for the terrycloth monkeys. These are the hours for those terrycloth monkeys. All right, so now we have our data correctly entered. So we're ready to tell SPSS, now that we have the data entered correctly, we're ready to tell SPSS what test to do. So for that, we go up here and we go to Analyze. This is the tab that we're going to use the most. So we go to Analyze, and then we go down here to Compare Means. That is the selection that we're going to use the most. Actually, that's where we're going to camp out for all of our remaining hypothesis tests. So once we decide that we're going to go to Analyze and Compare Means, we now have to choose which test do we want to do. And sometimes SPSS is going to be very friendly. Sometimes it's going to be not so friendly. I will point out the times when it's friendly and not so friendly. This time it's being very friendly because we are doing a single sample t-test, and lo and behold, it has something called one sample t-test, and it's friendly because that's the one we want. So we are going to click on one sample t-test here, and it brings up this one sample t-test dialog box. So in this dialog box, there's two things that we need to do. The first one is we need to select what is our test variable. Now that's going to be really easy because we only have the one variable. So your test variable is the raw scores. Those are the raw scores that you entered. And we are going to click on terrycloth here, tercloth, and we're going to use this arrow to move it into the test variable window. If we make a mistake, we can use the arrow to move it back. And we can move it back in. And we can move it back out. And we can put it back in. We can take it back out. So you don't need to do that. But that's how you get it into that test variable. The last thing we need to do, and this is the most important thing, this is the move where if you make an error, this is where you're going to make an error. This is the pitfall, okay? This is the red flag. This is something that you should double check every single time you do that, and it has to do with the test value. This test value here is what you're comparing your raw scores to. This test value here has to be your null hypothesis mean. It has to be the mean of the population under the null hypothesis. So in our study, if the null hypothesis was true and none of the monkeys preferred the terrycloth over the wire mesh monkey, then we determined that they would spend 9 hours with the wire mesh monkey and 9 hours with the terrycloth monkey. That is our test value. So we don't compare this test value to 0. 0 is not the test value. We want to know, do they spend 9 hours with the terrycloth mother, or do they spend more or less than 9 hours with the terrycloth mother? 9 hours is what we're comparing it to. So update your test value. Make sure that it is absolutely your hypothesized mean. That is what you need it to be. That is what we're comparing our raw scores to. Once we have all that set up, we have the terrycloth and the test variables. We have our test value equal to our hypothesized mean, in this case, 9 hours. Once we have all that, we're ready to go. We hit OK. And that quick, we have calculated our t-test. So double check with the numbers on the screen right now. We're about to go back to the PowerPoint. If you don't have those numbers pretty close to exactly those numbers, then you're going to want to go back, rewatch this part of the video, set it up again. You might be missing a crucial point. If you're missing numbers, if SPSS was unable to calculate certain tables, again, there was an error that was made. So you want to go back, rewatch the video, and try to follow the steps again. And if all that doesn't work, check the announcements, come by an office hour, and we'll get you all taken care of. But importantly, our t-test is completed. So what we're going to do now is we are going to take a look at how to interpret this particular output. So this is from, again, a previous version. These screen grabs are from previous versions. The table is set up exactly the same. There's just some slight cosmetic differences, so we'll be using this when we interpret our t-statistic. So what do we need to interpret this for? Well, we need to be able to do step 5. We need to be able to decide whether we want to accept or reject the null hypothesis. So we need to figure out where our t-score is compared to our cutoff score. Where is our sample t-score compared to our cutoff scores? So again, if the sample t-score goes beyond the cutoff t-score, accept the research hypothesis and reject the null hypothesis. If the sample t-score is within the cutoff t-score, we're going to do the opposite. We're going to accept the null hypothesis and reject the research hypothesis. So in order to get that information so that we can do step 5, we got to go back to our output, and we need to identify where we can get the information for step 3, for step 4, before we can go and do step 5. So let me zoom in on that so that we got that a little bit bigger so we can follow along. So we got 2 tables here, and you're going to want to use both of these tables. Now, the first one that you want to start with is that top table. So you can see that top table labeled one sample statistic. you can see right here, it lists the variable that was used to analyze it. So it lists our terracloth variable, and we want to check this to make sure that we entered in the correct data. So how do we do that? Well, the first thing we're going to want to check is that N. So that second column indicates how many scores SPSS was given. So we had 9 monkeys. SPSS is telling us that it has 9 scores. That gives us confidence that we didn't mess up when we were transferring data into SPSS. We take a look at the next column labeled mean. SPSS tells us the mean of all the numbers that you gave me, the mean of all the raw scores you gave me is 15.3. Very quickly, we can just take a look at our Excel sheet, calculate the average if we don't have it, and determine, yep, that's the mean of our raw scores. Once again, giving us that confidence that we've done it correctly. And the last thing that we can check is that standard deviation. So we could calculate the standard deviation of our raw scores, and we would see that it is 5.196, the same standard deviation that SPSS has calculated. And again, this is all just real quick little checks that you can do to make sure that you have put in the correct, you've transferred the data in correctly. All right, step 2, determine the characteristics of the comparison distribution. SPSS will do this. Let's see where SPSS has done that. So the first thing that we need is we need the mean of the comparison distribution. And we have already decided that that is 9, but just in case we forgot, SPSS lets us know that as well. So SPSS is telling us, oh, the test value that I used was 9. And this is another thing that you do want to check. Check that test value in that second table there. Make sure that it is your null hypothesis value. If it's not, scrap the output, go back, do it again. That is the mean for your comparison distribution. Now we need the standard deviation for the comparison distribution. We need that standard error of the mean, and lo and behold, SPSS has calculated that for us. So you'll remember in part 1, we did this by hand, and we ended up with a standard error of 1.73. SPSS didn't do it by hand. They did it much quicker and came to the same number. So as we go through these outputs, one thing that you're going to want to make note of is where you can find this information, because for different hypothesis tests, the information will be in different places. So I would highly recommend have these slides on hand, make notes in your own personal notes about where you can find the mean of the comparison distribution. That's your test value. Where you can find the standard deviation of your comparison distribution. That's the standard error of the mean in that top table. And we need one more piece of information. Where can we find the degrees of freedom for our comparison distribution? SPSS has us covered for that as well. So the column labeled DF, degrees of freedom, indicates that this t-test has 8 degrees of freedom. 8 equals 9 monkeys minus 1, and SPSS has calculated that for us. So that's our comparison distribution. Now what we need to do is we need to set a cutoff sample score or critical value. Importantly, SPSS will not do this for you, but it will help you. And it'll help you by giving you that degree of freedom. So we don't have to calculate out the degrees of freedom. SPSS has done that for us. And then we can take that degree of freedom and go to our table and once again use those 3 pieces of information to zero in on what our cutoff score is. So we're dealing with a two-tailed test that we got from the question. SPSS just told us that we're dealing with 8 degrees of freedom. So we go to that degree of freedom column, that first column on the left, we find 8 degrees of freedom. That's the row that we need. We have alpha level of 0.05. That's the column that we need. And where all of those intersect, that's our cutoff score. So we get a cutoff score of 2.306. It's a two-tailed test, so it's plus or minus 2.306. And now the last thing that we need is we need step 4. Determine your sample score on the comparison distribution. SPSS will do this for us. So our sample score is our mean score for our sample transformed into a t-statistic. And SPSS has transformed that into a t-statistic and put the number right there. So we calculated this out by hand, and it gave us, and we found out a t-statistic of 3.637. Here it is again, but this time SPSS calculated it. That's your t-statistic. That's where your sample is when you translate it into the comparison distribution. And just to kind of put this on your radar, we're going to start moving from statistics to probabilities. We're going to start moving from a t-statistic to a p-value, a probability. And just to kind of put it on your radar, SPSS will calculate that for you as well. And we'll see how to use this in upcoming classes. All right, so step 5, decide whether to reject the null hypothesis. If the sample t-score is beyond the cutoff t-score, again, draw these out until you get very familiar with it. This is the case that we have this time. So the cutoff score is 2.306. The t-statistic is 3.6. That is beyond the cutoff t-score. So we're going to accept the research hypothesis. We're going to reject the null hypothesis. If the other situation occurred, if the sample t-score was within the cutoff scores, it did not cross that line into the tails, it stayed in the body, we would accept the null hypothesis and we would reject the research hypothesis. So again, get that t-statistic, compare it to your cutoff score, draw your distributions out, and we can see that in this case, our sample t-statistic went beyond our critical cutoff scores, so we reject the null hypothesis. And SPSS leads us to the same conclusion, that the monkeys prefer the terry cloth mother. All right, so that was your intro to SPSS. Before we wrap up today, just a few things I want to point out. First off, the MyStatLab study plan. Keep working on those. We're doing the pretest. We're continuing to go on with the pretest. However, they will start getting much more challenging now, especially if you don't have access to SPSS information, if you and try the pretest without learning how to do SPSS first. So because of that, the MyStatLab study plan becomes more and more important. So make sure you're taking advantage of that so that you can do the pretests and use them for what they are meant for, which is the practice, without it impacting your GPA. And in terms of extra practice, you might have noticed we had some extra numbers on that Excel sheet. The data is there in the Excel sheet. The questions can be found in a supplemental PowerPoint slide, Week 12, Class 2 Practice, Chapter 8, Introduction to the T-Test. And what you're going to find is you're going to find demo questions that lay out all the information that you need. And then on the next slide, you're going to see the output that you're supposed to, that you want to produce. And then on the slide following that, you're going to see the answers to all 5 steps in each of the questions. So try to do them on your own first. And then if that doesn't work, do the check what the numbers should be, double check your answers. But this is where you can kind of practice using SPSS, get those SPSS skills so that you can become as proficient in SPSS as you are in Excel. So homework assignment number 10, you are now ready to go for homework assignment number 10, part 1. So part 1 is all about single sample t-test, what we were doing today. You're ready to go for that, so give it a shot. Make sure SPSS is working and give that a crack. As always, remember that MyStatLab study plan. And that is what I wanted to cover for today. So thank you for joining me on this very important lecture about SPSS and starting to do the t-test. This is what we've been practicing this whole semester for. We're finally down to the real deal. We're finally down to the real world statistics that professional psychologists use. And I'm glad you came here to join me, and I will see you next time. Take care.